Okay, so for this next lecture, we're going to be talking about electrophilic aromatic substitution. If you have an aromatic ring like benzene in the presence of a good electrophile, the first step in the reaction mechanism is exactly the same as if you would see an addition reaction across a double bond. The benzene ring attacks the electrophile, and you get the carbocation intermediate. Now, if this were an addition reaction, this next step would be your nucleophile coming in, attacking the cation to give you the addition product. In aromatic systems, we do not see this reaction. Instead, the nucleophile behaves as a base and removes the proton. The net result of this is that one of the hydrogens on the aromatic ring is substituted for by this electrophile. So now the first question is, why does this reaction occur to result in the substitution instead of addition? Well, so when the aromatic ring attacks the electrophile, it temporarily loses aromaticity. And if you remember, aromaticity is a very stable molecule. So temporarily losing it's okay, but if the nucleophile attacks the cation resulting in the addition product, that aromaticity is now permanently lost. And so the activation energy for this just way too high. So instead, you get the substitution reaction, which returns the ring to an aromatic state, much more stable. Okay, so substitution of benzene by a good electrophile is fairly straightforward. It does not matter which proton you choose. You basically always end up with the mono-substituted product. The issue with this reaction comes into play after you get mono-substitution, when you put a functional group on the aromatic ring. So we're no longer talking about benzene, we're talking about some other molecule. How does this functional group affect this type of reaction? Well, when you put a functional group on the aromatic ring, it affects the substitution reaction two ways. The first is in rate. That is, how fast does this reaction occur? Basically what we do is we set benzene as our standard, and we say if we put a functional group on the aromatic ring, does the reaction happen faster or slower than benzene? And then the second way in which this reaction is affected is what we call directional control or positional. That is, where on the aromatic ring does the substitution occur? So let's talk about the first effect, and that is rate. Does the reaction rate happen faster or slower than benzene? So the first thing we're going to do is we're going to define what our functional groups are. And we can classify our functional groups into two major categories. We can call them electron releasing and electron withdrawing. If we have a functional group on the ring, we'll just call it an electron withdrawing functional group. That's a functional group that withdraws electron density out of the ring towards itself. So then we ask the question, will those types of molecules have a rate slower or faster than benzene? And the answer is that it will be slower than benzene. And the reason, again, has to do with this very first step. The very first step is the ring acting as a nucleophile, attacking the electrophile. In order for you to be a nucleophile, you have to have electron density. And so if we have a functional group that is drawing electron density out of the ring, you're in essence decreasing the nucleophilicity of the aromatic ring. and those functional groups have rates slower than benzene. And so we tend to call electron withdrawing functional groups ring deactivators. And so the nice thing about having two basic categories, you've got electron releasing and electron withdrawing, when it comes to how do they affect. Well, we've already defined how they affect with electron withdrawing, and so that means that electron releasing are the exact opposite. These are functional groups that release electron density into the ring, they increase the nucleophilicity of the ring, and they have rates faster than benzene, and so these are often called ring activators. Okay, so how do these functional groups affect rate? Fairly straightforward, nothing too difficult in terms of trying to figure out how it happens and so forth. Now let's talk about the second one, and that's direction or position. So if we have our substituted benzene ring, and we do the reaction, there are three possible products that can form, and we're only talking about monosubstitution here. And so we can have substitution occur in this position. This is called ortho. We can have substitution occur in this position. This is called meta. And last but not least, we can have substitution occur in this position, and this is called para. So there are three possible products, and then the question then becomes, okay, if I have a functional group on the aromatic ring, what is the distribution of these products going to be? And there are basically two extremes to this. You can either have a 1-to-1-to-1 ratio of all three, or you can have 100% of one and 0 of the other two, or you're going to be somewhere in between those two extremes. Now, unfortunately, answering this, trying to figure out why we would get one particular isomer over the other, is a little bit more involved than trying to determine why it's a ring activator or a ring deactivator. So the first thing that we have to do is we have to look at this carbocation intermediate a little bit more closely. So let's just have substitution occur in the ortho position. So when it occurs in the ortho position, we get this initial carbocation intermediate. Now the thing is that in an aromatic system, this is not what we'd call a localized carbocation. That is, it's not stuck on this carbon alone. It's delocalized because of the conjugation of the aromatic ring. It can spread the charge throughout the ring due to some resonance stability. And so let's draw some resonance structures. So here's our first one, and then we get this one. Finally, we get this one. So you can see we have three resonance structures here. If we have substitution occur in the ortho position, again, we can draw some resonance structures. There's one. So with ortho substitution, we get 3 resonance. With with meta, we get 3 resonance structures. All right, now let's look at para. So here's 1. Here's 2. And then here's 3. Okay, so with the functional group on the aromatic ring, if you get ortho, meta, or para substitution, we get 3 resonance structures to help stabilize the carbocation intermediate. Okay, so now let's use this and try and, again, the whole purpose of all of this is we're trying to figure out which one of these particular isomers is going to be the preferred product during the substitution reaction. And so now let's put, instead of FX, let's call it an electron withdrawing functional group. And now let's define what an electron withdrawing functional group looks like. For instance, a very powerful electron withdrawing functional group is the nitro group. Okay, so if we have this electron withdrawing functional group on the aromatic ring, the nitro group, how does that dictate which one of these isomers is going to be produced? And what we have to do is let's specifically look at this isomer, or this carbocation intermediate. This carbocation resonance structure of the carbocation intermediate. Sometimes you have to remember it always gets a little bit crazy when you're trying to single out a resonance structure. This is not something you can isolate. It's only part of the whole. And every now and then it gets a little bit crazy when you're trying to talk about them and focus on them. So again, remember, we're isolating this, but this is really just an exercise because you actually cannot isolate it. So let's draw this resonance structure. Well, let's put the nitro group as the functional group on the aromatic ring. Okay, so with this resonance structure, we have a carbon with a full positive charge on it, and that is bonded to a nitrogen with a positive charge on it. And remember, in nature doesn't like positive next to positive. That's not going to be very stabilizing. So when you think about these resonance structures, remember, a resonance structure is something that helps stabilize whatever form that particular molecule is in. And so this is a cation, and we're asking, does this particular resonance structure help stabilize this cation intermediate? Well, with these first 2 resonance structures, the positive charge is on these 2 carbons, and you can basically say they're the same in terms of stabilizing the resonance structure. But this resonance structure, it exists, but it's not going to be as stabilizing as these 2. So when it comes to an electron withdrawing functional group, when you get substitution that occurs in the ortho position, we have 2 resonance structures that help stabilize it and one that's not so good at stabilizing it. again, it is a resonance structure, but we're thinking in terms of how well does it help stabilize it. And it just doesn't help as much as the other two. So now if we look at meta-substitution, well, with meta-substitution, that positive charge is never on the carbon attached to the functional group. So all three of these resonance structures help stabilize that carbocation intermediate, in essence the same. So you have three stabilizing resonance structures that help at all about the same amount. Now if we look at para-substitution, well again, these two resonance structures, the positive charges on these two carbons, but with this one, we are again in that situation where the positive charge is attached to the functional group. So if we draw that resonance structure out, again with our nitro group, we see that we have the positive next to the positive again. So just like in this resonance structure, it exists, but it doesn't help stabilize it as much as these two. So electron withdrawing substitution in the para position has two that help stabilize it, and again that one that is not as helpful as the other two. So with this information we can conclude that when you have an electron withdrawing functional group, not only is it an electron, or excuse me, a ring deactivator that have rates slower than benzene, they are also what we call meta-directors. That is, when you have an electron withdrawing functional group and you isolate the products, the dominant product in the reaction is going to be the meta product. Okay, now let's switch to an electron releasing functional group. Well, what is an example of an electron releasing functional group? And a good one is the alcohol. And again, in order to figure out how this affects the substitution, we again have to look at this intermediate. Now we'll draw this intermediate with the alcohol in place. Okay, so this is this intermediate with the alcohol as the functional group. Now, unlike this intermediate where we had two positive charged, that's not something that nature wants to have happen. The difference here is oxygen has these two lone pairs of electrons, and it can actually donate one of those pairs of electrons to form a fourth resonance structure. So with an electron releasing functional group, when you have ortho substitution, you have 1, 2, 3, and now 4 resonance structures that help stabilize it. Now again, we know oxygen doesn't like to be positively charged. So if you think in terms of, well, which one of these, helps more than the others, well then these 3 are going to be helpful more than this one, because we know oxygen doesn't like to have that positive charge. But it is still a fourth resonance structure. You have more resonance structures to help stabilize it than you do in like the electron withdrawing functional group. So with meta, again, because that positive charge is never on the functional group attached to the aromatic ring, we still only have 3. And finally, with para, we can draw that important resonance structure again. And so again, just like in ortho substitution, we are going to get that fourth stabilizing resonance structure. So para gives us 4. So electron releasing functional groups are known as ring activators, and they are also called orthopara directors. Okay, so I do want, before I continue, I want to focus on one kind of special class of ring activators, and these are the alkyl groups. So for instance, let's have ortho substitution occur with something like toluene, and let's draw this third resonance structure here. Now, alkyl groups, toluene, ethylbenzene, etc., these are ring activators and they are orthopara directors. But unlike something like oxygen, where it doesn't have, the methyl group doesn't have those lone pairs of electrons. So how do we get stability from this particular intermediate? And if we look at this carbocation resonance structure intermediate, we see that this is a tertiary carbocation. And so these two resonances help stabilize that carbocation intermediate fine. This one helps it stabilize it really fine, because in a tertiary carbocation you have hyperconjugation and so forth. So that's how things like methyl and ethyl and all your alkyl groups can be ring activators and orthopara directors, even though they don't have the lone pair of electrons to form that fourth stabilizing resonance structure. Okay, so with the electrophilic aromatic substitution experiment, we're going to divide it into two halves. So the first half is going to deal with how do functional groups affect rate, and the second half will look at direction or positional control. And so the first is the rate experiment, the rate of bromination. And we are going to brominate 5 different molecules. We're going to brominate phenol, 4-bromophenol, anisole, acid anilide, and diphenyl ether. Okay, so these 5 molecules, we are going to add bromine, and the general reaction is this: ARH plus Br2 goes to ARBr plus HBr. So this reaction first is very similar to one experiment we did a few weeks ago in the stereochemistry experiment, or in the free radical substitution experiment, where we brominated different arenes and we tried to figure out which one would be faster. So it's the same basic experiment, only in this case we're looking at the electrophilic aromatic substitution rather than free radical substitution. So one of the things that is very different about this particular experiment is the solvent. And the solvent is 15 molar acetic acid. And that's an odd solvent. Normally when we think about solvents, it's water, ethanol, methanol, dichloromethane, things like that, but not 15 molar acetic acid. So the question is, why are we using this particular solvent? Well, the first rule whenever you're using a solvent is that everything has to be soluble in it for the reaction to occur. That's kind of it, it's a must. If the solvent doesn't allow for the solubility of one of the reactants, the reaction doesn't happen. So everything is soluble in this particular solvent. But there are other solvents that would work as well, dichloromethane to name one of them. So why specifically are we using 15 molar acetic acid? Well, when we did the Grignard reaction, we talked about the fact that that particular solvent also needed to be aprotic because of the fact that the Grignard reagent was very basic. So the solvent had to fulfill another role, and that was it had to make sure that it didn't react with the reactant. We're kind of taking a slight reverse course in this particular choice. Because if you remember, I talked about that very first step in the reaction mechanism is the aromatic ring attacks the electrophile and temporarily loses aromaticity. It's not what we would call a small activation energy. It's temporarily losing aromaticity. That's pretty high. Now, if we took bromine and dichloromethane, the reaction would work, but it wouldn't necessarily happen in a relatively reasonable amount of time. So one of the things that we have to do is we want to speed it up, and that's what the acetic acid is doing. So if we take bromine and we just kind of draw it out, and we add something like a proton, which 15 molar acetic acid has lots of, we can form a partial bond with this proton in one of the bromines. Well, what that does is that shifts electron density from this bromine towards this bromine, making this bromine a little bit more positive, having a partial positive charge associated with it. In other words, we're making it a better electrophile. So by using 15 molar acetic acid, we are in essence activating our bromine, if you want to call it that, allowing this reaction to occur within a reasonable amount of time. And so that's the purpose behind using the 15 molar acetic acid. And so this reaction is very easy to do. It's just setting up the test tubes, running them and looking for the disappearance of the red color once the reaction is run to completion. So that is the rate of substitution, rate of bromination in the electrophilic aromatic substitution experiment. The other half is what we're calling the nitration of bromobenzene. So bromobenzene, we're going to add the nitro group to it. And there are a couple of different ways to nitrate an aromatic ring. We're going to take kind of the most straightforward approach. We're going to take concentrated nitric acid and mix it with concentrated sulfuric acid to produce our electrophilic nitronium ion. Now, bromine is a weak ring deactivator. And if all you have heard about electrophilic aromatic substitution prior to this lecture is what I said today, then calling it a weak ring deactivator would mean, okay, now we're talking about a meta-director. So we would expect to see the dominant product as the meta product. However, halogens kind of break the rule. They're the ones that screw everything up. And a halogen is, although it's a weak ring deactivator, it is also an ortho-para-director. So ortho and para are going to be the dominant products. And the reason for that is that bromine has these lone pairs of electrons, unlike the nitro group and things like that, with which it can donate to form a fourth stabilizing resonance structure. Okay, so the ortho and para products are going to be the dominant products, and when we look at the actual distribution, we see that we get about 37% ortho and about 62% para. Now, one of the things that we would like to discuss about these two numbers is, of course, they don't add up to 100. There's a missing 1%, and that 1% is, in fact, meta. So one of the things that's important to understand about electrophilic aromatic substitution and directional control is, when we say dominant product, that's not to say we see absolutely none of the other isomer. It's a minor product, and in this case, it's about 1% of the product distribution. But again, the dominant product distribution is going to be ortho and para. Now, of these two, we see that para dominates about 2 to 1. And of course, the reason for that, when we look at bromine and we look at the nitro group, these are two very big functional groups. They're going to have some steric strain associated with them. Plus, you have the dipole moments such that we have partial positively charged carbons bonded to each other. And so ortho substitution has a lot against it. And so we see that it's about a 2 to 1 ratio. In this particular case, we're not interested in the ortho product. We only want to isolate the para product. And we can take advantage of the individual dipole moments to help separate them. Because of the ortho orientation, there is an overall net dipole moment. Whereas in the fact that the para position have these in kind of in opposite directions, that means the para product is less polar than the ortho product. And we can separate these two by a simple recrystallization. So we're going to run the reaction. We get the crude product. We do a simple recrystallization in ethanol, and then we can isolate the para product once the crystals precipitate out of solution. It's a fairly straightforward reaction. One of the biggest issues, of course, is the formation of the electrophile, and that's why we are again using these two very strong acids. When you mix sulfuric acid and nitric acid together, sulfuric acid is actually a stronger acid than nitric acid. So if we draw nitric acid, so here we have nitric acid. If you add sulfuric acid to nitric acid is actually going to act like a base, and it will be protonated. And so this ends up being a water molecule, and this is the nitronium ion. This is our electrophile. So that's how we can generate the nitronium ion, by mixing nitric acid with sulfuric acid. This reaction works exceptionally well. The only real issue you have to worry about is controlling the temperature. You don't want it to get too hot. Even though the ortho product is going to be about 1/3 less than the para, about 1/3 of the product, and then the para product is about 62%. One of the issues in terms of the reaction is temperature control, because if you allow the reaction to get too hot, what ends up happening is you can run the risk of getting dinitration. So we could end up with this particular product, which is of course something that we absolutely do not want to have happen. And so that's why it is important to not allow the reaction to get too hot. The biggest thing when doing that is, of course, when you mix the two acids at the very beginning, make sure that you add sulfuric acid to nitric, not the other way around. And again, just simply control the temperature. Product analysis is straightforward: melting point, percent yield. And most people get somewhere around 50%. It's a microscale experiment, so as with all percent yield calculations, it's always, as long as the chemistry works, and this is one example of a chemistry reaction that works very, very well. As long as the chemistry works, it's almost always about transfer. How careful are you when you're transferring the solid from one container to the next, and so forth. So that is the end of the electrophilic aromatic substitution lecture. If you have any questions, by all means email me, or of course you can always attend one of the office hours and ask your question there. Alrighty, we'll see you next time. Bye-bye.